Today we are going to start the second chapter. It is called first order partial differential equations. In this chapter we will study first order partial differential equations and Cauchy problem associated to that, and what are the possibilities in terms of existence, uniqueness, and maybe non-existence as well we will discuss. Now in today's lecture what we are going to discuss is how the first order PDEs appear, how they arise, and the Cauchy problem, initial value problem and initial boundary value problems, what are they, we will discuss briefly. So the outline for today's lecture is the first point is how the first order PDEs appear. We will see two situations, one of them is going to be a physical situation and the other one is within mathematics, mathematical situation. And then we define these terms, Cauchy problem, initial value problem, initial boundary value problem for first order PDEs. We look at three examples which suggest us what happens or what can happen to a Cauchy problem in terms of existence of solutions, uniqueness. And then we look at a simple first order PDE for which we consider IVVP, that is initial boundary value problem, and we study what are the possibilities there. Now how the first order PDEs appear. So first order PDEs arise in many situations. We are going to just see two instances. The first one being as a mathematical model for a physical phenomena. In fact what we are going to see is not really a physical phenomena, it just models the traffic on a highway, and then we see as equations satisfied by some mathematical objects. So this is the physical model which we are going to look at today, is a mathematical model for traffic flow. So in this model we are going to have two main ingredients, we will briefly introduce them. So one of the most fundamental physical principles is what are called conservation laws or balance laws, and one encounters them already in course of mechanics, where we would have seen conservation of mass, energy and angular momentum. So we are going to derive a PDE model in a simpler situation. We call it simpler because no a priori knowledge of anything is needed, including physics. Okay. As I told you, we are not going to do really a physical model, it is going to actually a model of the traffic flow which can be easily understood. So let us consider an express highway without any intermediate entry or exit points. It has one entry point, one exit point. You can't join the expressway in between, or you can leave. Both possibilities are not there. Leaving and joining is not possible. So the traffic, what we mean is, let us say vehicles, let us say cars, just to refer very easily. Assume that vehicles are moving in a straight line. As we know, vehicles do not move straight lines, they will be overtaking one another. But what this means is that this gives us a way to identify the highway as an interval in R, and it actually physically means that overtaking is not allowed. Maybe the expressway is very narrow, so you can't overtake. Now let rho denote a car density at a point x in R. Yes, the road is not infinite, but then we are going to finally specialize to certain intervals. Okay. So at the time instant t. What does this mean? Car density means what? We can get the number of cars by integrating with respect to x. So let a be less than b, then the number of cars in the interval a b, in terms of the highway it may be a stretch between a point A and a point B, at time t is given by the integral of rho over the interval a b. Now we need to know how it changes. So the instantaneous rate of change at time t is given by the derivative of this number d by dt of the integral a to b rho x t dx. But who is really responsible for this change? It is the cars which are entering at the point A and leaving from the point B. Therefore, the same number is given by the influx of cars at A minus outflux of cars at B, which is QAT minus QBT. Both are same numbers because we made this assumption of no entry and no exit. Thus, we have this balance law. So, both these quantities are balanced. Therefore, d by dt of integral a to b rho xt is equal to QAT minus QBT. That is the balance. So, the balance law is now d by dt a to b rho xt dx equal to QAT minus QBT. Now, we are going to modify the right hand side. The right hand side we write it as an integral. So, if you use this fundamental theorem of calculus will give you QAT minus QBT. So, interchanging the order of differentiation and integration in the first term d by dt is outside the integral, we can take it inside. Yeah, of course, we know that this is not true all the time, it is not allowed, one needs justifications, but this is where I say no bargaining ends at the very first instance. So, do not ask that questions right now, they can be asked later. So, now once the d by dt go inside the integral, the balance law becomes a to b dou rho by dou t equal to minus integral a to b dou q by dou x. Now, let us take the RHS to the left hand side and then the balance law becomes integral a to b of this quantity dou rho by dou t plus dou q by dou x equal to 0. Now, this is true for every a and b such that a less than b. In other words, you have integral of certain quantity is 0 over every interval a b. It means that integrand has to be 0. This is an exercise in analysis. We would have encountered many such situations. For example, if you take a continuous function integrate on any interval a b and if the result is 0, then the continuous function has to be 0. And there are generalizations of this, which may be, let us say, a locally integrable function. If you integrate on any set and the integral is 0, then the function must be 0. So, these are two typical instances where we can conclude this. Now, what remains is the equation has a rho, that is what is the traffic about, we want to study about this, but there is an unknown quantity q, the flux, it is not known. Therefore, we need to model that. Therefore, it is reasonable to think that q depends on x time t and the density of cars itself, that is rho. So, q can be thought of as a function of x, t and rho. Okay. This kind of proposition of what kind of a function it is of the variables x, t and rho is what is called a constitutive law. Of course, there will be as many models as the number of constitutive laws. So, constitutive law models how q depends on x, t, rho. Consider a simplest constitutive law which is given by q of x t rho. Since x t is not involved in this formula, I have not written x t. So, q of rho equal to c rho, where c is a positive number. This means the flux is proportional to the number of cars. So, substituting this in the balance law, what we get is dou rho by dou t plus c times dou rho by dou x equal to 0. This equation is called a linear transport equation. This is a linear equation is clear because the unknown quantity rho itself does not appear. What appears is their first order derivatives dou rho by dou t and dou rho by dou x, it appears with the power 1. So, this is a first order linear equation, c is a constant. Therefore, it is a linear equation. Why is it called transport equation? Something must be transported from somewhere to somewhere. It must be from some time t equal to something to future times. So, in deriving this model, recall that there were two main ingredients. First one was balance law and second one is a constitutive law or constitutive relation. Balance laws are very general, constitutive relations model the specificness of the situation, in this case of the highway. So, in our model we use the constitutive relation as q rho equal to c rho. In general, q may be more general function of x, t and rho. In that case, the balance law becomes this dou rho by dou t plus dou by dou x of q of x t rho. If you expand this, you will get this one. So, you need to differentiate x appears here as well as in rho. Therefore, need to differentiate q with respect to the first variable and differentiate q with respect to the last variable and differentiate rho with respect to x. This is a chain rule. So, chain rule is a very important rule that one must be very comfortable when you want to do anything with differentiation. Okay, so, this is a quasi-linear equation, it is a first order PDE. Quasi-linear because this may depend on rho, okay. That is why it is a quasi-linear equation. Now, we are going to model a highway where entries and exits are there in between. That means, we will see now how the earlier model derived is going to change. So, the entries and exits are also called source and sinks in the PDE literature. So, let f denote the source sink density at x at the time instant t. Now, the model becomes this is the rate of change. Earlier this was just equal to the flux, but now this will also have the source sink term, which is this integral a to b f x t dx. Now, bringing everything to one side, what we get is integral a to b of certain thing is 0, and this is true once again as before for every a and b such that a is less than b, both are arbitrary. Therefore, the integrand must be 0, which will be the case whenever the integrand is continuous or locally integrable, but it is not unreasonable to assume that integral of over any set is 0 implies the integrand is 0. Now, let us look at how the first order PDEs appear in a mathematical context. So, we are going to see an example. Consider a 2 parameter family of surfaces. Surfaces, in fact, what we are going to consider is surfaces which are graphs z equal to f of x, y, a, b. What are a and b? They are some parameters varying in some intervals. So, it is a 2 parameter family of graphs of functions. Now, we want to derive a differential equation satisfied by this family, and we are saying partial differential equation. Therefore, what we can only do here is to differentiate this with respect to the 2 independent variables x and y, and this is the expression we get. Now, assume that from these 2 relations you can solve a as a function phi of x y z x z y and the b as a function of psi x y z x z y. Now, question is it always possible? These are all questions, but here if it is possible we will go ahead and do the next step. What is the next step? I am going to substitute for a and b these formulas inside this. Then what I will have is z equal to f of x y phi of x y z x z y comma psi of x y z x z y, which will be a nonlinear partial differential equation. In general. Now, let us look at a specific example where the functions are taken to be x minus a whole square plus y minus b whole square. A and b are parameters varying in real numbers, both of them are real numbers. Now, what are these surfaces? What does this equation represent? Represents cones, family of cones. So, differentiate this relation with respect to x and y and eliminate a and b. In other words, solve for a and b in terms of rest of the things. So, here it is very simple, a equal to x minus z x by 2, b equal to y minus z y by 2. Now, substitute the values of a and b inside this expression, z equal to x minus a whole square plus y minus b whole square, which is the equation of the family of surfaces. Once you do that and simplify, you get this following PDE. Zx actually stands for dou z by dou x. Okay. If you want to write in terms of x, you can write dou u by dou x whole square plus dou u by dou a whole square equal to 4u. Now let us see what are the problems which go by the name of Cauchy or initial value or initial boundary value problems, what they are. So, let us consider a PDE f of x, y, ux, ux, uy equal to 0. It means I am considering a PDE in 2 independent variables. Throughout this chapter, we are going to consider first order PDE in 2 independent variables, and then we will also say how theory changes if you have one more variable. So, x, y are independent variables, u is the dependent variable, these are the derivatives. So, there are 5 quantities here. So, f must be defined on a subset of R5, and that we denote as omega 5 is a subset of R5, and you have a function, and then this will then define a partial differential equation. So, what is a Cauchy problem? Given a space curve gamma in R3, that means you are given a curve in R3 which is described parametrically by this, that is x, y, z equal to fs, gs and hs as s varies in some interval I, and f, g, h are C1 functions on the interval I, and such that the projection gamma 2 of gamma to xy plane. Where is gamma? It is in R3. So, it will have xyz coordinates. Now, you project it to the xy plane, you will have xy coordinates, okay, that is x equal to fs and y equal to gs, that is the curve gamma 2. S in CMI. It is a regular curve. What that means is f dash g dash do not vanish, that means does not become 0 0 at every point of the curve. If one of them is 0, other one is non-zero. If f dash is 0, g dash is non-zero. And find a solution to the PDE such that u of fs equal to hs for s belonging to a subinterval of I, In other words, a part of gamma lies on this surface S denoted by S. Equation is set of all x, y, z such that z equal to u x y. On this surface, a part of this curve, given curve gamma lies, right. Gamma coordinates are fs, gs and hs. So, third coordinate hs must be equal to u of first 2 coordinates fs, gs, that is the condition here. We are not requiring that this should happen for every s in I, we are only asking for s belonging to subinterval of I. So, this can be thought of as a local solution. So, this gamma is called a data curve or datum curve or initial curve. Note that this problem actually makes sense only if gamma is subset of omega 3. What is omega 3? It is a projection of omega 5 which is in R5 to the first 3 coordinates x, y, u. Okay, what is initial value problem? It is a special type of Cauchy problem. Initial means there is something like a time in the problem, and initially means at some particular time in the past something is happening, and then you are interested in studying the equation for future times. So, therefore, one of the variables will have an interpretation of time, let it be y, there is no loss of generality in assuming y, x would equally do the same thing. So, the y variable has an interpretation of the time variable, and the datum curve now lies in the zx plane given by this x equal to s, y equal to 0, z equal to hs. In other words, what we will be asking is actually u of x comma 0 equal to h of x should be satisfied. This is what we are asking for the Cauchy, for the solution of the PDE. So, find u of x t such that u t plus 2 u x equal to 0 and u x 0 equal to sin x. Okay. Parametric representation of gamma. What is gamma? X equal to s, y equal to, or here t equal to 0, it is not y, it should be t, because y has a interpretation of time variable. So, you can as well write t. So, t equal to 0 and z equal to sin s, and s belongs to R. That is a parametric representation of gamma. Now we do not know how to solve this for now, but given a formula we can always check that it is a solution. So, u of x t equal to sin of x minus 2t, if you quickly differentiate you will get that ut plus 2x equal to 0, it solves the initial value problem. So, when t equal to 0, this formula u of x 0, what will we get? U of x 0 will be sin x. So, initial condition is satisfied. So, we can think of like this okay. So, this is the time variable, this is the u variable, this is the time, this is x. At t equal to 0 you are given a sin x like that. Okay. So, you have to imagine this in the ux plane, and then at t equal to half what you will have is the formula, from the formula what we have is it is sin x minus 1. So, u of x comma half is sin x minus 1. It just means the graph of sine has been shifted to x equal to 1. Suppose this is 1, this is pi, right. So, this is pi by 2, so this is 1.5 already. So, it's somewhere here. So, the graph will look like this, it's moving. Okay. So, it is difficult to write for me in 3 dimensions, but you should imagine that the graph of sin x has moved, graph was like this at t equal to 0, now it has shifted to 1, but now this I am writing at t equal to half. So, it just moves back. So, okay. Now, initial boundary value problems. Once again initial is there, so there should be a time. So, the unknown u in this PDE x t u u x u t equal to 0, I already made this change of y to t because the word of initial y boundary. So, this equation or what you want to study, it may not be relevant for all x in R. It may be that it is relevant only for x positive or maybe for x in some bounded interval a b. In such cases, imagine the first case, if it is meaningful only in R plus, then x equal to 0 is a boundary of R plus, right, boundary point. And if you are studying x in a b, then there are 2 boundary points, x equal to a and x equal to b at these points. So, you need to prescribe some conditions there. That is what is called initial boundary value problem. Okay. Yeah. Now, let us look at a picture illustration. So, this is the case where the domain is R plus, x belongs to R plus, therefore, you have boundary at x equal to 0. So, you prescribe this G, of course, initial condition you prescribe. Now, when you are doing initial boundary value problem, when x belongs to this interval a b, you have to give initial conditions and also give boundary conditions. So, now let us look at 3 examples, 3 guiding examples for us Cauchy problems, because you can understand the entire theory by using these examples. Before that, let us ask the following question: does every Cauchy problem have a solution? Good question. This question sounds like a very familiar question that we asked earlier. Does every problem have a solution? This is not the first time we came across such a question. It was asked many times, and many times we even had a complete answer. For example, system of linear equations where Ax equal to b, where A is a square matrix, there we understand completely. Under what conditions you have existence, what conditions you have uniqueness and non-existence. Now, let us ask the same question in some few well known situations for us before. Solutions of polynomial equations in one real variable. What about that? A polynomial may not have a solution. Polynomial equation x square plus 1 equal to 0 has no real solution. It can have exactly one solution, let us say x minus 1 equal to 0 or x into x square plus 1 equal to 0, they have exactly one solution. Then you can have finitely many solutions. Let us take very simple x minus 2 into x minus 3 equal to 0, right. Any finite number, let us say a1, a2, an, you write x minus a1 into x minus a2 into x minus an equal to 0, precisely these are the solutions a1, a2, an. But you cannot have infinitely many solutions for polynomial equations. That is because of fundamental theorem of algebra. It says given a non-constant polynomial, it has exactly the same number of roots as the degree counting multiplicities in the complex plane. Therefore, in real numbers may be less than or equal to that. Then solutions to initial value problems for ODEs. This is where we have seen Picard's theorem and Peano's theorem. In Peano's theorem, if the right hand side, let us say y dash equal to fxy, let us write once. This is the kind of equations for which we have a theory, and this is the initial value problem. If f was continuous, we had Peano's theorem which said there is a solution. In addition, if f is Lipschitz with respect to the y variable, then Picard's theorem told us that it has a unique solution. And when you do not have unique solution, you can easily show that you have infinitely many solutions. That is the situation about ODEs. So, this is under sufficient conditions that we have proved these theorems. So, if these sufficient conditions are not satisfied, we have no idea what will happen, anything may happen. You may still have uniqueness even though the right hand side function f is not Lipschitz, that is a possibility. Now, solutions to boundary value problems, we have a Bernstein theorem under some sufficient conditions. It guarantees that a second order ODE boundary value problem posed for that will have a unique solution, at least when the Dirichlet data. Okay. This if you do not if you have not studied IVPs, you can look at any good book on ordinary differential equations, you will find. Then solutions to transcendental equation, this is the most difficult one. You have no, it is not like polynomials. So, you have to worry with each separate equation is a different story. There are once again sufficient conditions. Okay. Now, let us see what are the examples. So, the examples we are going to see are of Cauchy problems. In these 3 examples which demonstrate all 3 possibilities. In this case, what are the possibilities? You have a unique solution, infinitely many solutions and no solution. Of course, another option is that finitely many solutions, which I have not thought about. Let us take that up in a tutorial session, that discussion. So, what does this mean now? It means that we do not expect existence uniqueness theorem for free for any first order PDE, we do not expect. So, only under some special assumptions, in other words sufficient conditions, we can expect such theorems, which was true in all our earlier cases. Let us say in the ODE initial value problems or boundary value problems, that is true. Okay, let us look at a very simple first order PDE. It is ux equal to Cu, C is a constant. We will look at a special constants later, C equal to 1 and minus 1 later on in the case of initial boundary value problems. Here C can be any number, a real number. So, it is posed for x in R and t in R. You do not see t in the problem. So, it is actually ODE, and from our ODE knowledge we can solve this. Any solution must satisfy this equation uxt equal to u0t into e power cx. Now, let us look at 3 Cauchy data. What are they? First one is u of 0 t equal to t, second is ux 0 and here also ux 0. That means initial Cauchy data is given here on t axis, here in other 2 cases given on x axis. Now, using this expression we will get this u0 t you wanted, t is supplied. So, t into e power cx, that is a solution. In this case ux 0, that is t equal to 0, that is u 0 0 into e power cx, but u 0 0 must be 1. Therefore, any function of t such that t of 0 is 1 will do our job, it will be a solution. T into c e power cx is a solution whenever t 0 equal to 1. Here if u is a solution, then what is expected is sin x must be a multiple of e power cx. That is impossible, because sin x and e power cx are always linearly independent as functions on any interval that you consider. So, message is that Cauchy data 1 unique solution, Cauchy data 2 and 3, one case you have infinitely many solutions, for Cauchy data 3 there are no solutions. So, 3 possibilities have been exhibited here. Now, why the Cauchy problems behave differently? PDE was the same, ux equal to Cu. Then what is different? U was prescribed on t axis, we had uniqueness, and when u is prescribed on x axis, either we had infinitely many solutions or no solutions. Therefore, we ask the following question: Is t axis something special for the equation, or is it x axis which is special for this equation? The reason for the first question is because we have uniqueness. Second question is we have many possibilities. So, who is really special here? Because special people have to be taken care with a lot of special care. Okay? We will see that later on. So, the answers we will see later as we study the first order PDEs. Now, let us look at a simple first order PDE for which we pose IBVP and a few observations. We will not be dealing with this further in our course. So, the fact is that general solution of ut plus cux equal to 0 is given by uxt equal to phi of x minus ct, where phi is any C1 function which is arbitrary. Of course, what is that? T equal to 0, ux 0 becomes phi x. So, this phi is nothing but the initial solution, initial condition. Okay. Now, initial boundary value problem, as I told you, there will be a PDE posed in the first quadrant xt, x positive, t positive. Initial condition is given and there is only one boundary point, namely x equal to 0, therefore, u of 0 t is also prescribed. Now, uxt equal to f of x minus ct, because see here we said phi is the initial data, right. So, therefore, here also we have initial data. So, how much we can, this determines the solution. So, f of x minus ct will be a solution surely, no problem, but whenever x minus ct belongs to the domain of f is defined only for greater than or equal to 0, therefore, this determines a solution whenever x is bigger than or equal to ct. We will see a picture soon. Now, on the line x minus ct, the solution u will be constant, it will be f of k, x minus ct equal to k is greater than or equal to 0, therefore, this formula applies and uxt equal to fk, it is constant. Now, let us look at the case where c equal to 1, this is the picture. So, this is ux 0 fx, this is u0 t gt, and u in this region this the line x equal to t is in dots. To the right side of that, this region corresponds to x bigger than or equal to t, there f of x minus ct. Similarly, you can show that here it will be g of t minus x, that will be solution. So, on this line t minus x equal to k, solution will be gk, and on this line x minus ct equal to k, solution will be f of k. So, initial condition determines u in this region and boundary condition determines in this region. Now, what about line x equal to t, what will happen? So, let us write the formula, this is the formula that we said. Now, if this has to be a solution, it has to be differentiable. The first question is it differentiable? So, this is a candidate solution we say, because we have derived certain possible formula for the solution. That is why we propose a candidate, we need to verify that it is indeed a solution. So, that requires that fg must be C1 functions and compatibility of the data is needed, f0 must be equal to z0, f dash 0 equal to minus z dash 0. How do you get these compatibility conditions? You simply ask at points where x equal to t, write down the differentiability property of u of xt, that will tell you that this condition has to be met, otherwise it will not be differentiable. So, once you have these compatibility conditions, that implies that u has to use a C1 function. So, and IBVP has a unique solution. Now, the case c equal to minus 1 is totally different. Now, the line is x plus t equal to constant. This line touches both the boundary as well as the initial data. So, and once again f must be constant on this line, solution must be constant. Therefore, this line touches at k 0. So, it should, the value on this line should be fk, and it touches here at g 0 k. So, the answer must be, the solution must be g of k. So, on this line the solution is both f of k and g of k. What if f of k is not equal to g of k? There is a problem. Okay. This means that g cannot be prescribed independent of f. This initial boundary value problem has no solution in general, but there are some generalized notions of solutions where under some other condition they admit solutions. Okay. So, we will not be discussing such generalized notions. This is in the normal notion of a solution. There is no solution, that is very clear from the formulae. So, let us summarize what we did today. We have derived a first order PDE to model traffic flow and also modified to account for sources and sinks, namely entries and exits in the expressway. And we highlighted the roles of balance law and constitutive relations in deriving mathematical models. This is how models in let us say continuum mechanics will be derived. These are the two things which are at the heart of any modeling. And then through 3 examples we understood that number of solutions to a Cauchy problem depends on the relation of the PDE to the datum curve. And then we saw IBVP problems need not have solutions. So, thank you.